So you have to order up a whole bunch of these, a few samples at a time, and unpack them and test them for sounds and feels. Eventually you'll vaguely find that a few are good, a few are bad, and you kind of start categorizing them and you whittle them down. Basically, what I was left with was a couple that are good, one's waterproof, one's not, and the rest are kind of weak or nah. So having tested those switches at the time, I found a couple that I liked, and I used them in these little hacks. I hacked these into my EPS system or another version of these. And those are just the tiny, tiny tack switches in a 3D printed case with a flexible element. I didn't understand what made these feel so good, but on my bike, they didn't feel as positive. They didn't feel as strong and reassuring. They easily led to potential misshifts. And yeah, basically, I mean, they work, but they're not the greatest. Here on my tabletop, they feel good, but out there with road vibration, with all sorts of these interfering effects, they didn't feel as good. So this is a test 3D printed demo thing that for a couple of buttons, and similar enough to the end application that they work. If you look at it, they kind of rock on an angle. They use the same switches that I use in here, and yeah, the feel is kind of the same, but the tonality changed and a few other things changed, but basically the rocking of the switches was the main problem here. I hadn't really put everything together on what was wrong with the feel of these switches. On my tabletop, they worked great. On my bike, they didn't. So then I reused the switches to try and make a little mock-up, and the switch feel changed. The tactile feel didn't, but part of how things are organized inside meant that these buttons kind of didn't have much to guide them. So when I pressed them, they like to rock on an angle. And I tried many variations to align things, to make things better, to make them push straight down. It didn't feel exactly like what I wanted. So enter my old Nintendo Pro controller. There's a few things we can learn from game controllers. The first thing is button placement. These buttons are designed such that you can pretty much access most of them just from your thumb. You can access 4 buttons from your thumb without a lot of movement. You're not like having to, some people will do stuff like this, but you can, in this case, BY rock, or you can BA rock, or you can, X is kind of the outlier. It's the one that you have to lift your thumb for. If we measure them, what we'll find is that they're pretty much exactly 16 millimeters center to center for every single button. And we can also learn that the buttons themselves are about 10.5 millimeters in diameter. I don't just have a Pro controller, I also have an Xbox controller. What we'll learn from here is the buttons are about 14.5 millimeters, and they are 10 millimeters in diameter. So I know between 10 and 10.5 is probably the ideal button size for a thumb tactile operation. But I also know that I can more easily rock and access 2 buttons on the Xbox controller. So if I need 2 button access, I probably want the 14 millimeters. But that whole wobbly button thing, yeah, there's a little bit of wobble here, but not very much on the Xbox one. So if we take them apart, we can probably learn how they do it. And I don't think I actually took mine apart. I actually looked at teardowns. This is a pain to take apart, but it's doable. This is apparently multiple layers of boards, and it really sucks to take apart, so I didn't do that. But we can turn to the internet and things like iFixit for that information, kind of like how I turn to the FCC filings for people's schematics. So I'm a bit of a liar here. I did take apart the Nintendo Switch controller. This is all the button arrangements, and you can see there's two types of buttons. There's our standard tacks, and I've got some of these somewhere, ones that look almost identical, and we have, these are like for the dome switches, they short out. However, what we want to really look at is these buttons, and so try not to drop anything. If you look closely in here, there is a guide. So the button is rather long. It has several anti-rotation features, so that length allows it to move up and down, prevents rocking. And then the anti-rotation helps guide it, but also kind of helps that verticality as well. These were not as good as the Xbox ones, possibly due to longer travel, possibly due to how their rotation, or just, I think, more related to the tolerance of them. But it's those features, it's the anti-rotation and the cylindric shape that really contribute to a good vertical stability. These switches are renowned for very good stability, very low friction. So we can actually disassemble these fairly easily to find out what is inside. So what's inside one of these Cherry switches? Well, when you push down, this part is doing some guiding, but this part is also doing guiding. So the top and the bottom both act as guides. The ones in the bottom are spread apart. They also act as an anti-rotation mechanism. And you can see as it's up, it pulls the contact away, and as it drops, it just, the force actually pushes it back. And there's a spring to keep this pushed up that is preloaded. So we have common elements in both. We have a rectangular feature to act as a guide, and then we have anti-rotation elements on either side that also further acts as a guide. When it's in here, it's guided, and the lower element also guides it. So we're back to the general solution is some sort of a large primary guide for verticality and an anti-rotation guide, or at least mechanically those are the elements that lead to a premium feeling button. So just like I went through those tack switches, I could have done the same with all of these. These are effectively what's inside. You can see they're little domes. And it's just a curved piece of metal cut to a specific shape with legs on the side. And when it presses down, when you press it down, it touches a contact in the center. Now there's a whole bunch of these, different force ratings, they have different sizes, different codes. The WTDs are different than the GXs. The GXs are different than the squares. And they all have little variations of feel and sound, and some of them, like the GX series, are actually stackable. So this opened the door for some different waterproofing solutions, whereas with the regular encapsulated tack switches, I had limited options. There could be 40,000 different designs. Once you whittle it down, there's 2,000 or 3,000. Once you say things like you want only SMD style, you don't want this, they don't want right angles, you're down to a couple of hundred. And then when you say, I need waterproofing, you're down to like 10, 20, maybe 30, but a lot of them are no good. They're too low force, they have mushy feels, or they require other aspects. So these allow different options for waterproofing. They may not be better, but there are way more options for a snap dome shape that you can use directly on a PCB then there are snap domes, and there can be more variations with these, and you can do things like stacking them. So you've got your little clicking element here, and have a 3D printed housing, and it goes over it. Imagine there's a button in here, but that button's going to move around. Now, I also alluded to the fact that these things can be waterproofed. So pre-cut, they laser cut these into strips or squares. We'll just grab a square for now. Polyester film, it has a adhesive that actually cures, sort of cures. So I know where it needs to be approximately, and I did a terrible job. So you can actually use a little bit of heat, 40 to 50 degrees, will actually activate and heat up the acrylic adhesive, smooth it down, and now that's going to actually be a lot tougher. Put in our switches. So this board was designed for these switches, but with the new mock-ups I unified for testing everyone with the same kind of design, they're not centered, so no big deal. Just like this one, I just solder them off-center to whatever free pads there is. It's not like they're electrically connected, so it doesn't really matter. So a lot of learning from game controllers. So the first thing is this tubular structure really helps keep the buttons aligned, but these little dimples, these anti-rotation dimples, made a real improvement in feel. Wobbly buttons are a big hazard to a quality button. And this is what you end up with, or a whole bunch of these little 3D printed housings with just switches that you're testing for feel, and you're just trying to press them over and over and over again. And you know, in this case, I was talking about how the alignment tube, yeah, there's a little bit of rock there, but nothing big. But the anti-rotation actually really helps. So, I mean, it's advisable to try it on different surfaces even, or in different orientations, or different rates. Something might feel good for a double click, but terrible for a triple click. Or the glove test. I mean, if it's something used outside or with gloves, in this case, it changes the feel, it changes the sound. There you build up a lot of these. So all the combinations that you want to test, all of these buttons, and you probably won't know what to do with them. So that's where we get to on the next bit. When you have a lot of different choices between something and you need to come up with a approach of deciding something semi-subjective, then one of the easiest methods that has been used in specifically engineering a lot that I've seen is decision matrix. And a decision matrix, there's several different variations of this. Basically, I like the variation of this that compares and ranks only 2 items at a time. If you're given 2 choices of which is better, then eventually with enough data of evenly but randomly showing them to people, for instance, and testing them, that you tend to get a ranked consensus. We just need to have our samples all across the top, and in this case they could be 3 dome switches. They could be 3 different types of switches. Then we have what we're rating them on. You can skew the results by skewing the weightings here. For instance, in one application, what we perceive as the feel may be the most important, and seldom used with gloves, so that feel without gloves becomes the most important. But feel doesn't necessarily work without sound. So what we might be able to say is it's an 80-20 split for these 2 categories to gloves, and from feel to sound, it's probably say 3 to 1-ish. So it might end up being 60 and 20 and add to 100%. We could have an application where over 50% of the time, say in an oil patch situation, you're using gloves, maybe 80 or 90%. So the feel, which may encompass glove and non-glove feel, but the operation may encompass gloves. You may have various different categories. You can break this up into several different ways. And you'll see later on how I broke it up into 4 categories, kind of breaking up feel into 2 different categories and gloves as a glove usage to kind of encompass all 3 of them, but for that use case. There's several ways you can do this. You can do a ranking method. If there's only a few, it can work out easily, because ranking 3, 4, 5 things, it's not that hard. Sometimes you'll get 2 that are close, and consensus between different people may sort it out. But the comparison method tends to work very well, because if I say A and B, I can sit there and I can press A and I can press B and I can swap them, pressing B and then A and then B, and I can come up with a which is better. And in this case, let's just say that A is better. So A gets a point. Even in mine, some of them were so close that I gave them half a point each. But we do a comparison of A to B. Now let's do A to C. So you do the comparison again. You're sitting there back and forth, and A wins out. Not surprising if they're not evenly spaced on the spectrum of good to bad, but now we have to figure out, all right, where's the rest? Well, we've already compared A and B, so there's no point to do B to A. It's the same thing, just reversed. So what we want to do now is we want to compare B to C, and that will give us all of the combinations. With B to C, let's say C is better than B. So you sat there and you press them back and forth, back and forth, back and forth. Now we get to sound, same thing. In some cases, you can do them all at the one time if something is clear, but you kind of want to go line by line, rerunning this test by test. And you find out, you know what? A and B are really close, but I'm giving the edge to B. And A to C, A definitely wins out, and then B to C, it's a tie, so it's 0.5 on gloves. You can't just assume gloves. Again, you replicate the application, get some gloves, get various different gloves. Don't just test it with one glove if glove is a scenario, and rank them. And what we might come out seeing is that, A to B, B wins. A to C, A wins. B to C, B wins, just for sake of randomness. So basically what we can do is then we multiply this all through to get individualized kind of a point score, and that point score changes. So don't worry, it's all like if we added another button, the maximum points will go up and the maximum score will go up. So hopefully I've done my math here correct. And what we do is we just multiply the score by the percentage, and we can get 1.2, 0.2, 0.2, and then we sum them all up. And as we can see in this scenario, A comes out ahead. But with this weird uneven balance and uneven weighting, what we see is that B and C are actually tied. That's actually kind of interesting because C has such a great feel. It has much better sound, but B just wins it on use with gloves, and it could be something specific about it. Generally, this probably wouldn't happen. Something like B would not come out ahead. What if we want to add more? Well, you'll have to recalculate this, but we can just add a D and add a D. And it's really simple because then all we do is we run through every single combination of D with A, D with B, D with C. And that will actually sum into this. It'll change the maximum values, but the subjective ratings will always be the same. So if you want to go and add another button to your test later on, then you can easily do that. So what I did is I did all my snap-downs, and then I thought, I should really test my latest switch. Okay, and I added that in. So I had about 10 of them, and I added an 11th. Then I thought, that original non-waterproof one, I like the feel, and I still like the feel. Let's see where it rates. So let's go and look at what those results actually came out to be. This here is the spreadsheet I was talking about. It has the 4 categories. They're all rated 25, 25, 30, and 20. These are the snap domes, and they were all tested as a group, and then later I added this category for the waterproof button and this one for the original button that I used on my EPS hacks in the first mock-ups. And as I just explained, you just compare one to the other. Whoever wins gets a point. They can tie. As you can see, this one has tied with something. But if I was to add another one, right now the maximum, a perfect score for comparisons against everything else would be 11. If I added a new one, that maximum will go to 12. So it changed the points. So these are just summations to make sure I haven't missed anything. Same here, summation to make sure the points add up to 100%. So when I do all those comparisons, multiply them through down here, and I colorize them for largest number of the whole everything to the lowest. So worst is red, best is green, just conditional, your standard conditional formatting. And what you'll see is a few stand out, and the rest kind of middle of the pack, and a few terrible ones. So these 3 here look really good. This one's starting to get middle of the pack, middling. This thing, as you can see, I marked really bad. And basically, stacking domes is expensive. I had other people try it, and I think this might be a little too heavy. While it's good for me, someone with smaller hands or producing less force with their fingers and thumbs might not like it. This looks like a possibility, but it's stacked domes again. This is rated up there. But the interesting thing is when I added this waterproof switch, and I had done those comparisons, it was right at the beginning of this video, it felt like a good switch. And then to compare them to all of these switches, it rated really lowly. But then when I took my absolute original non-waterproof switch that I had used on my EPS hack, it's interesting. It's kind of in the middle of the pack for sound and glove feel, but low end on force and decisive moment. And so those accidental shifts, verified. Aspects such as the strong feel, it's weak. It doesn't take a lot of force to move it. So basically, like, this could be improved. This would get a much better score in the event that I could get a higher force one. But for the EVQ 3 PLA series, that's it. That's the max. There is no greater force available for that model. So this is the limitation I butted up against. It's a good switch, but it's not a high enough force. So what did I learn from all this deep dive into buttons? Starting with the game controllers, that was where my first learning beyond just trying a bunch of different tact switches came from, was understanding that the element you physically interact with, being some sort of like a plunger mechanism, its stability is probably one of the most important things that leads someone to feel that a product is premium or not premium. Having some travel and have it moving vertically specifically, fending off rotation in some way, and not having like lateral play or angular play. Those really increase, I'll say, some level of consumer confidence, or even just my confidence that it is a premium, well-conceived product. Now, from that, we saw that one of the aspects of the Shimano shifters that I didn't like was more the force curve, but part of it is kind of in the stability, is that you could move them around without them ever doing anything or interacting with anything. And that was due to their low spring force before they actually hit a tact switch. So that brings us to the force aspect. There must be an initial force, so you shouldn't feel some movement before that initial force is overcome. That kind of leads to the no accidental pressing. You don't want to just bump up against something and the trigger force is so low that it doesn't, you accidentally shift, or you trigger a light, or you trigger whatever, you need to be able to avoid the accidental presses. So initial preload is a solution to that in some applications. But you want a consistent force slope, and you can implement that several ways. It's a little harder with direct actuation of domes, but you can choose your dome such that the force is sufficiently high enough, the vertical movement is within the range you want, or you can amplify that range by doing things like using a lever arm mechanism. But then usually have to do what Campagnolo did, you stack the domes to increase the force, because if you double the movement, you half the force, you triple the movement, you 1/3 the force. So you have to be able to tune that force in order to get that movement you want. It has to be a consistent force slope. So as you're increasing force, you may increase displacement to proportionally, and then it drops off, you need to hear an audible click, and you know it shifted. So there's the tactile feedback and the auditory feedback. With Shimano, what we got was a very flat curve because of the weak spring. Yes, it was preloaded, but it was a weak spring. And then it would ram into a heavy tack switch. So you could play with it, and I got several people to try it and unable to actually shift it until I told them, push harder, which is not a very good sign for such a premium product, a product found on $7,000 and $8,000 bicycles. So we have a relatively low feel here. They need to bottom out to give an indication that, okay, I've done my job, but you want it to be consistent there. And as I just mentioned, the auditory feedback. It is interesting how much we actually depend on that click to indicate to us that you've pressed a button of some kind. So I mean, if you look at microwaves, for instance, they tend to default with a beeper because their buttons are so bad. It's the same kind of thing here. It affects the feel. And the easiest example of this is the newer iPhones with the Taptic engine. When you use the home button physically doesn't move. It doesn't click anymore. And what it does is it uses a linear resin actuator, a smaller version of what was found in the Nintendo Switch Pro controller. It gives a little buzz in a quick pulse that makes you feel like tap. But it also on default generates a click noise, and they work in tandem. An interesting thing to test is headphones, loud headphones, and press that button and see how it feels or how it changes the feel. You'll be actually quite surprised. That leads us to what generates that noise. If it's artificial versus natural, like in the case of snap domes, you need a way of getting that sound out. And this doesn't have to be highly intentional, but you do have to take in consideration that how it sounds free in the air versus in a chamber versus in a different design are all going to be different. And if you really want to go deeply into this, you can probably tune those to resonate or do other things to damp harsher harmonics. But you just want to be aware that you're testing in a design that is similar to your final, which brings us to the last point, is test. And test and replicate in both the situation and with the, gloves or vibrational things, or, if it's on a big vibrating machine and it's always running and you want to push that button, that's going to be a different scenario than if something is flat on a table in a quiet environment and you're pressing the button. So you have to be aware of these and test in the situation. For me, I've gone through multiple revisions, adding elements of this, tuning my force, tuning my displacement. I've given some thought to the sound, and I've tested it in multiple scenarios where I want to use it. And I've tested it how I'm going to use it. Gloves may be a part of it, not a huge part, not a huge potential, but there is an edge case, and it was tested with that. I've gone through most of this, and the worst part of this is I can't tell any of you what it's for. So with that, thanks for watching the probably weirdest over-examination of such a simple piece of technology. Thanks.